Another feature that we'd like to find in graphs is not a circuit, but just a what's called a spanning tree. And a spanning tree is just a connected graph that touches all of our vertices, but we don't have any circuits. We don't want to include edges that we don't need to in order to connect everything into one piece. So that's what a spanning tree is, and we are going to be interested in the minimum cost spanning tree, which is a spanning tree that has the smallest total edge weight, meaning what's the cheapest way to connect all of our vertices into one hole, using our edge weights. So let's go ahead and look at an algorithm that tells us exactly how to do that. This is Kruskal's algorithm. This is extremely similar to the sorted edges algorithm. The only thing that changes is we don't want to, we're totally fine with having vertices of degree 3. We're fine, no matter what the degree is, it's fine. The only thing we want to avoid is creating circuits, okay? Because if we created a circuit, that means we've got some edge that's unnecessary, because all we're trying to do is connect everything. Let's go ahead and do Kruskal's algorithm here on this example. Okay, so using our sorted edges algorithm, essentially, Kruskal's algorithm just says find the smallest edge, and that here is from LA to Seattle. Okay, so that's our smallest. Our next smallest is from Chicago to Illinois, $75. Okay, our next smallest is the 85. So we add that. Our next smallest is from LA to Chicago. And notice now we have visited every vertex, and that means we are done. Okay, this here is our minimum cost spanning tree. Notice that there is a way to get from any city to any other city using the path that we've created. Okay, and there's no unnecessary paths in order to do that. So that's our minimum cost spanning tree. Let's do another one. Find the minimum cost spanning tree for this graph. We start with our smallest edge. Smallest cost edge, that's from A to C. Okay. Our next smallest is actually both the C to D and A to B. And we can add both of those because neither one of those creates a circuit. So we're good doing that. Okay. The next smallest is the 3 from B to E. Okay, adding that, we are done because we have now visited every vertex, and that's our only goal in our minimum cost spanning tree. Now, when we've got just a table that shows us our edge weights, we can do the same thing that we did with our sorted edges algorithm. We're going to go ahead and just cut out half of our values because we don't need them. Okay, we have all of these connections represented in the top half. And we're going to go ahead and just draw, kind of in a circular pattern, our vertices, A, B, C, D, and E. And we begin by adding our smallest weight edge. That's going to be this 20, A to E. Okay, so we've got that. Our next smallest is 24 from B to E. Okay. Our next smallest is 25. That's B to C. Okay. And now I want to show you a little trick. Notice that I've now visited every vertex except for D. So all I need to do now is look at D and pick the cheapest way to connect D to something. And notice I could do from D to B, or I could do D to E, and they're actually both the same price. So either one is fine. I'll go ahead and do D to B just to keep it interesting. Okay, so there is a minimum cost spanning tree that uses those red circled edges. Let's go ahead and do it again here. We've got now 6 vertices, and we just need half of our table. And we're going to draw out our 6 vertices kind of in a circle. So I've got A, B, C, D, E, and F. Okay, and we start by adding our cheapest edge. Our cheapest edge here is this 11 from D to E. Go ahead and add that. Our next cheapest edge is the 12 from D to A. Okay, our next cheapest edge looks like it's the 17 right here from D to F. Go ahead and add that. Our next cheapest after the 17 looks like it's this 20 right here from D to C. Good to do that. Notice that we're no problem here having a vertex of degree more than 2. Okay, we're just finding a spanning tree. Now at this point I have visited every vertex except for B. And so this is the point where I can skip ahead and say now I just need to find the cheapest way to connect B to any one of these. So I can just look at my B column and now I can look down here. If I want this cheapest way to connect to B is from B to E, okay, which is that 24. I also see that right here. Okay, so from B to E, go ahead and make that connection. There is my minimum cost spanning tree. Every vertex is connected into one graph, and I have no unnecessary connections. All right, now that we've done several examples of that, why don't you go ahead and try the minimum cost spanning tree for this graph here, okay, and see what spanning tree you come up with. So we start with our smallest edge here. The smallest edge is this 11. Go ahead and add that in. After 11, the smallest is the 13 from B down to G. Our next smallest is the 14 from E to A. Next smallest is from E to F. We're at 15. And now notice I've visited every vertex except for C. And so now all I need to do is find the cheapest connection from C to one of the others. And that is going to be this 17 right here from E to C. There's my minimum cost spanning tree for this graph.